All right, hi everyone. So in the last video, we finished our discussion of exponentials and logs, and I think I mentioned at the end that we were going to be starting a brand new topic with this lesson. So this is going to be about the unit circle, and this is really the beginning of our discussion of trigonometry, which we'll be talking about for probably about 6 weeks or so. Now, I want to start by saying that trigonometry can be studied in terms of circles or in terms of triangles. Those are kind of the two main perspectives. And really, a pre-calculus class could cover the circle version first or the triangle version first, and either way would work out. We're going to talk about the circle version first. So if you have friends who are also taking pre-calculus, they might be getting these topics in a different order. But the textbook that I like to reference uses circles first, and I like this order of topics. All right, so beginning trigonometry here. All right, let's get started. All right, the unit circle. So first of all, I'll say that trigonometry sounds intimidating. It sounds like it's going to be difficult, but it's really not that bad. And in this section, we're really just going to talk about circles and points and things like that. So I want to start by saying, consider the set of all points x comma y that are a distance of 1 unit from the origin 0, 0. All right, so let's draw a picture here. We're talking about the xy plane. We're talking about the origin. So yeah, let's get a picture going. We will draw something like this. There's x, there's y, there's the origin at 0, 0. Let's go ahead and mark some points we know that are a distance of 1 unit away. For example, this point here at 1, 0. I know that that's a distance of 1 from the origin, right? Distance from 0, 0 to 1, 0, that distance is 1. You could also go in the other direction. You could have this point here that's over at -1, 0. Or you could go vertically. You could say, I know this point up here is a distance of 1 from the origin, so that would be at 0, 1. And we could also go down here, this point here at 0, -1. So those are 4 points, 4 easy points that I know are a distance of 1 from the origin. Now, there are also other points, right? Because we could go in a diagonal direction, a distance of 1 unit. And above it, it's asking us to consider all points x, y that are 1 away from the origin. So for example, how about I do this? Let's say I go in this direction. Can we say that maybe that would be about a distance of 1? Right? I don't want to go all the way up here to 1, 1. That would be too far. That would be a longer distance. I'm trying to go about this, like the length of this line segment should be equal to this. And we could also go over here instead, or we could go here, go here. We get lots of points that we could imagine, or maybe go in this direction. Get a point down here. And the idea is that you could keep coming up with other points that are a distance of 1 from the origin. Like maybe there's one over here, maybe there's one over here, maybe there's a bunch of them over here. And really, there's going to be infinitely many by the time we're done with this. So I'm going to say that these are some points that fit this description. But if we were to truly consider the entire set of all points a distance of 1 from the origin, We'll draw it on a separate picture. If we do all points that are a distance of 1, we would have all the points in between these, right? We're starting to create a circle shape. All right, you know what? Circles are hard to draw. And generally, when I teach pre-calculus, I usually draw some really nice circles. But this time, I'm kind of hunched over a document camera, and it's a little bit more difficult. So bear with me if my circles don't look perfect this semester. It's a lot easier on a whiteboard. And right now, I'm kind of hunched over my desk trying to like manage a microphone and a document camera and my notes and this page and my pens and my mouse. So anyway, that's a good enough circle. That's a good enough circle. Let's move this up a little bit. So how do we find the location of these points? Here's a question. You know, I said the coordinates for 4 of them because they were on an axis and I knew what the coordinates were. But like, what about this point up here? Do we know this is something, comma, something? Do we know what, comma, what? So here's the idea. We can find these points. Using the distance formula. We're talking about a distance of 1. What's the distance? Here, let me move the page up a little. What's the distance from x comma y to 0 comma 0 of just any point? X comma y to 0 comma 0. Let's put it in the distance formula. It would look like x minus 0 squared plus y minus 0 squared, square root over all of that. And we want this distance to be 1. So we know what the distance is supposed to be. Well, x minus 0 simplifies to just x. Y minus 0 simplifies to just y. So this is like x squared. This is y squared. How about this? Let's square both sides. I don't mean square root both sides. I mean we are squaring both sides. Raise both sides to the 2. The left-hand side becomes x squared plus y squared. The right-hand side is 1. And we get this simple little formula. X squared plus y squared equals 1. And that leads us to a definition. Definition. The unit circle. I'm going to underline that. Is the circle of radius 1, centered at the origin, in the xy plane. Its equation is x squared plus y squared equals 1. So the unit circle is the set of all of these points that make up this shape. And all of the points that make up this shape satisfy this equation, x squared plus y squared equals 1. That's why we call it the equation of the circle. By the way, we could point out here that a circle is not x. Y is not a function of x, right? Y is not a function of x. We cannot write this as like f of x equals or y equals some function of x because this fails the vertical line test. So this is not a function. But that's okay. It's still a set of points. We could still talk about it as a set of points. We can still talk about it as an equation. And we can still talk about it as a graph. We're going to try not to call it a function. There are other shapes in math like that too. Now, we know already we said some points on the unit circle. And just to be clear, the points that make up the unit circle are the things along the perimeter. It's not like we're not shading this in. It's not the points on the inside of the circle. It's just the things that are a distance of 1 from the origin. And some of the points that we know were 1, 0, 0, 1, -1, 0, and 0, -1. Those were the ones that were on the x-axis or y-axis, and we can kind of tell just by looking at the picture. Now, if we want to find more, finding more specific points on the unit circle, we can use the equation. First of all, looking back at that picture, and I don't want to move the page around so much, but you've probably got that in your notes by now. Looking at the picture of the unit circle, it looks like there should be a point, or maybe 2 points, that have an x-coordinate of 1/2. So I'm going to try x equals 1/2 and see if I can figure out what the y value would be. Let's try this in x squared plus y squared equals 1. So we get 1/2 squared plus y squared equals 1. We're going to solve for y. So we get 1/2 squared is 1/4. We get this. I'm trying to solve for y, so I'm going to move the 1/4 over, subtract it, get 3/4. And now, in order to solve for y, I need to take the square root of both sides, and that means I get a plus or minus the square root of 3 over 4, 3/4. But I think there's a nicer way that we could write this, plus or minus. When you do the square root of a fraction, you really need to do the square root of the top and the square root of the bottom. Well, the square root of the top, square root of 3, we'll just leave that alone. But the square root of the bottom, the square root of 4, we should simplify that to 2. So we can write this as the square root of 3 over 2, where we've changed the 4 to a 2, but now the square root symbol is only on the 3. That's a little bit simpler. So let's do a quick Scratchwork unit circle. We're going to be drawing Scratchwork unit circles for the next few weeks, so we want to get used to that. Here is 1, and here is 1/2. And we just found that there are 2 points on the unit circle with x equal to 1/2. There's the one up here. There's the one down here. And those points are 1/2, comma, negative square root of 3 over 2, and 1/2, comma, positive square root of 3 over 2. I'll label them up here too. I can tell which one is the negative one and which one's the positive one, right? By which quadrant they're in. 1/2, and this is positive square root of 3 over 2. Quick side note, some textbooks refer to points like these as, they'll put a p in front, p of this and p this, where the p just means point. And I thought I would mention that in case you see that while you're studying, but in class, typically I'm not going to write the letter P to represent a point. Typically, I'm just going to write the coordinates x comma y with parentheses around them. And we understand that this is in reference to a point. If you have learned the way with writing a P in front or writing some other letter in front, that's perfectly fine if you want to write it that way. I just usually won't. All right, so there's already some questions that we could answer. So I'm going to show you a question with a few parts, and I'm going to do the first part for us, and then I'll give you a minute to try some of the other ones. So determine whether or not each point is on the unit circle. And I'm going to give a few points. I think from the picture of the circle, you can tell there's infinitely many points on the unit circle, right? Like that perimeter, you could always find more points if you tried to like draw every little dot. There's infinitely many, but that doesn't necessarily mean that everything in the XY plane is on the circle. There's certainly points floating around that are not on the circle. So we can get some good sort of yes or no questions. How about I put 3 of these and give me a minute to write them all, and then give me a minute to do the first one for us. And then after that, I'll have you try B and C. Okay, so let's do that. So I will go through part A, but I'll give you a chance just to write that down. So these are going to be yes or no questions, but it's kind of implied that we should also show our work, right? Yes or no, and show work to justify your answer. Let's see if we can probably answer each one of these like directly underneath the problem. I think we can do that. All right, so part A, we're going to check to see if this satisfies the equation of the unit circle. Does x squared plus y squared equal 1? So for these numbers, that would look like 3/5 squared plus 4/5 squared. And I'm checking to see whether or not this simplifies to 1. So 3/5 squared, you square the top and the bottom. So this is 9 over 25. And then over here, you square the top and the bottom. So that's 16 and 25. Those fractions have a common denominator, so I'd like to add them together. 9 plus 16 is 25. I get 25 over 25. That equals 1. I'll put a little check mark next to it. And the answer is yes. Yes, because it satisfies the equation of the unit circle. X squared plus y squared did, in fact, equal 1. If it equals anything else, then the answer would be no. So why don't you take a minute? You could pause the video and try part B and C, and then I'll talk about those. Okay, part B is 3/4, comma 3/4. I think if we just take like a quick look at the unit circle picture, or maybe even like the picture we drew earlier that was bigger, it looks like there might be a point on the unit circle around there, right? Because there's one, there's an x of 1, there's a y of 1. 3/4, 3/4, it looks like there might be a point on the unit circle around there. So let's check, does it satisfy the equation? 3/4 squared plus 3/4 squared. We're going to see if that equals 1 or not. Okay, square the top, square the bottom. When you do this, in some of these problems, you'll already have a common denominator. In some problems, you might have to make it a common denominator. But yeah, 9 plus 9 gets added. we get 18 over 16. Uh-oh, that does not equal 1. Does not equal 1. So the answer is no. In fact, you could say that it almost equaled 1, like 18 over 16. Like, it's pretty close to 1. And that's why I thought that it looked like 3/4, 3/4 would be pretty close. Because the answer we got is a little bit bigger than 1, 3/4, 3/4 is kind of a little bit outside of the unit circle. Still almost on the circle, but a little bit too far out. So no, it's not on the unit circle. What's this next one? -6/7. Oh, so I don't know if we can really tell this one by looking at the picture, but it's okay to have a negative x coordinate, a positive y coordinate. You know, that could be on the unit circle. Let's just put this into the formula and see what happens. You know, looking at the picture might help us estimate, but the formula is going to tell us a definitive yes or no. Does this equal 1? So when you square the top, -6 squared is positive 36. And 7 squared is 49. When you square the top and bottom of the other piece, the square root of 13 squared is 13. The square root of 7 is 49. This is a common denominator, so we can add it up and make one fraction. 36 plus 13 is 49, exactly. So this does exactly equal 1, and the answer is going to be yes, that point is on the unit circle. All right, so that's one type of problem you could see, just some yes or no questions. And you can see now that, you know, if we give you an x comma y, you could check whether or not it's on the unit circle. Just be careful with fractions and squaring things. Next thing we want to talk about are called terminal points. Terminal points. So suppose we start at 1, 0 and travel along the unit circle counterclockwise for a distance of how far do we want to go? It's going to depend on the problem. So let's use a variable here. We're going to go a distance of t units. Before I even draw anything, can you imagine doing that? We start at 1, 0. We travel along the circle counterclockwise for some distance. Maybe the distance is 2, maybe the distance is 3. Okay. The point we wind up at is called the terminal point. Determined by t. Seems reasonable. We wind up at some kind of point. If t is small, then we travel a small distance around the unit circle. If t is large, we travel a large distance around. But eventually, we've gone that far, we stop, and the stopping point is called the terminal point. I'll show you an example. So let's, as an example, consider t equals 2. And I said we're going to be drawing a lot of scratch work unit circles. So draw a quick xy plane, draw a quick circle centered at the origin of radius 1. And we are suggesting that this point 1, 0 is the starting point. And in our discussion of terminal points, 1 comma 0 is always going to be the starting point. So why is that the starting point? The simple answer to that is for what we're going to be doing over the next few sections, a starting point just needed to be established, and the consensus, the agreement is that this is going to be considered the starting point. So what we talk about is kind of based on this starting point. And why do we go counterclockwise instead of clockwise? It's just because it was designed this way. It's kind of the agreed upon direction for the definitions that we're going to have coming up. I mean, there's nothing particularly special about clockwise or counterclockwise. But anyway, how do we go to around? This is a curved distance. It's kind of easy to measure things in a straight line. It's hard to measure things when they're on a curve. I could use the idea that this right here, I'm going to try to draw like kind of lightly. This right here is a distance of 1, right? I know that this is a distance of 1. So what would it look like to go on around this curve for a distance of 2? How about we try to go a distance of 1 first? How about I go like that, maybe? Maybe that's about a distance of 1. Here, I'm going to put a little mark there and say that that's what happens if I've gone 1 unit. And now let's try to go another 1 unit, see where we wind up. Maybe about that far. We're kind of estimating when we draw this. I guess if you wanted to be like more accurate, you could get out like a piece of string and measure it. But I'm going to say that we've gone about 2 units of distance in along this curve. Oh, and we wind up at some point. I'm going to shade this in really dark. That would be the terminal point. So we have a starting point and we have a terminal point. In this case, the terminal point, I'm going to tell you I found that this is approximately negative 0.416, comma 0.909. So it seems like different t values would take us to different terminal points. Okay, here's a question for you. What value of t takes us completely around the circle? Once, to wind up back where we started. I.e., to a terminal point of 1 comma 0. That's the starting point. And I'm asking, what would t need to be to go around once and stop at 1 comma 0? Let's draw a picture. Scratch work unit circle. Doesn't have to be perfect. Just good enough circle to get the right idea. All right, we're going to start here. Starting point, 1 comma 0. We're going to travel some distance t in a counterclockwise direction. Let's do the same thing we did on the previous one, where we kind of try to figure out, like, 1 unit, 2 units. Looks like this is going to be more than 3 or 4. How about we start by going let's say here's about 1. Here's about 2. That's kind of where we stopped last time. But now we want to keep going. Let's figure out, what does t need to be? Get all the way back to the beginning. If we go again, let's say this takes us almost to touch the x-axis, but not quite. And then 1 more. We still have not gotten back to the start yet, so 4 is not enough. Let's keep going. That's about 5. 6 gets us to about here. This is an approximation here. I think a little bit more than 6. Somewhere between 6 and 7. I think if we went 7, we would pass the starting point and be going on like a second lap around. So 6 plus a little more. 6 plus a little more. So the answer to this question, what value of t does this? Would you believe that it is exactly 2 pi? And 2 pi is approximately 6.28. I kind of tried to go 1 unit at a time, and it looked to me like maybe it is a little bit more than 6. But another way that you might know this is if you remember the formula for the circumference of a circle. So this happens to be the circumference of a circle with a radius of 1, because the formula for circumference is 2 times pi times radius, and the radius is 1 in this case. So we could also say that t equals pi takes us halfway around, right? To the terminal point. What would the terminal point be if we went halfway around? Something comma something. Oh, look at this. It looks like when we were going around, I went 3, and then like a little bit more than 3 would have gotten us over here. That's what would happen if you went a distance of pi, a t distance of pi. It would take you halfway around the circle. The terminal point would be -1 comma 0 on that opposite side. Now, what we want to do at this point in our discussion of the unit circle is we want to be able to find terminal points associated with a few different common t values. We've already found that if you used a t value of 2 pi, we know what the terminal point is going to be. If you use a t value of pi, we know what the terminal point is going to be. What if you use half pi or 3/4 of pi? Like, that's the types of questions that we want to answer next. All right, let's move the page up. So I have a question for us, and I think I'm going to talk us through these because some of these can get kind of tricky when this is new to us. We are going to find the terminal point. So it's something comma something on the unit circle, and we are going to be given the t value. So t equals pi over 2. T equals 2.5 pi. And t equals pi over 4. That last one is tougher. Let's talk about each of these. Solution. Let's draw a scratchwork unit circle for each one. I think that's going to help. And we're going to use what we said above. Like this is based on what we already know. All right, scratch work unit circle. I know that we said just a minute ago that t equals pi takes us halfway around. This is half of that. Half of halfway around the unit circle, right? So like halfway would take us over to here. We would like to go half of that, so we're going to go counterclockwise until we get to here, and we've gone half of halfway around. I guess you could say we went a quarter of the way around the unit circle, and we wound up here. The t value that we did was pi over 2, and the point that we got to, I'll write it underneath, is easy to see because it's on the y-axis. It's the point 0, 1. So that is the terminal point for that t value. Part B, 2.5. Well, above we said that t equals 2 pi takes us all the way around the unit circle to the starting point. So what is 2.5 pi going to do? It's going to go even further. Here, let's draw the unit circle. All right, here's what I'm going to do. I'm going to start from our starting point, and I'm going to go counterclockwise. So let's start going around. All right, how far have I gone now? So far, I've gone pi over 2. Keep going. Or you could say I went 0.5 pi. All right, how far have I gone now? I've gone pi. Keep going, that's another half pi. Keep going. Okay, I've wound up right back where I started, so I know that I've gone 2 pi. This problem wants us to go a little further than that. We went 2 pi around, and I need to go an extra 0.5 pi. An extra 0.5 pi is going to take me to here and stop. Right here. That extra 0.5 pi is just like pi over 2, right? Because dividing by 2 is the same as multiplying by 0.5. So we wind up at the terminal point, 0, 1. We did an extra lap around the unit circle, but all we really care about now is what is the point that we're stopping at. So this right here should show you that in these types of problems, you could have 2 different looking t values that actually take you to the same terminal point. You could even imagine, like, what if I had a larger t value that went around the unit circle a bunch of times, lots of times, and then still stopped here? That could happen. Now, t equals pi over 4 is a little tougher. Let's see what we can come up with. I'll tell you it's not going to be 0, 1. Pi over 4. Let's think about, that's not the best looking circle, but all right, whatever. We'll work with it anyway. Let's look at part A. Part A was pi over 2. Can you see that pi over 4 is exactly half of that? Pi over 4 is half of pi over 2. It says a 4 on the bottom instead of a 2 on the bottom. So we want to go half this distance. Half the distance we did in part A. So go to about here and stop. And we're trying to find the coordinates of this point. Now, the t value that we used to get here was pi over 4, but that's not the answer. The answer is something, comma, something. Let's figure this out. It doesn't look like it's going to be 0, 1. It's not. It doesn't look like it's going to have a 0 or a 1 for either of the coordinates. Let's do a little work for this. So let's figure this out. Here, section these off. I guess we're done with those. I'd like to say notice at this point, at this terminal point on the circle, x and y are equal. Do you agree with that statement? That the x comma y, that the x and the y are the same thing. Why am I saying that? It's because of the nice sort of symmetry that we get with circles. Also, I think actually you could argue that this point looks like it is on the line y equals x. This is the line y equals x. So y and x are equal to each other. So the formula for the unit circle, x squared plus y squared equals 1, could be rewritten in this case, for this problem, as x squared plus x squared equals 1, because x and y are equal to each other. This is going to help us figure out what x is. And if x and y are the same, then really we just need to figure out what x is. Y is going to be the same thing. So this would be 2x squared equals 1, or x squared equals 1/2. I'd like to take the square root of both sides. When I do that, I'm going to get a plus or minus sign. X equals plus or minus the square root of 1/2. Now, we're not totally done yet. Let's think about this. First of all, let's try to rewrite this in a nicer way. Square root of 1/2. I've said that when you take the square root of a fraction, you could do the square root of the top, square root of the bottom. I know the square root of the top is just 1. The square root of 1 is 1. So we could just put the square root on the bottom part. And in fact, a little scratch work here. Sometimes in math we don't like leaving square roots in the denominator. We say that we would like to rationalize the denominator. We can fix this up by multiplying it by the square root of 2 over the square root of 2. Technically, you're allowed to do that because it's just multiplying by 1. When you do this, it simplifies the denominator to just be 2. And it means that the numerator is the one that's going to have the square root in it. So we just got plus or minus the square root of 2 over 2. Is that the answer? Well, the answer is supposed to be a point, x comma y. Let's look back at this picture. Is x plus or minus the square root of 2 over 2? No, x is positive, right? X is definitely positive. Like here's positive 1, This is in quadrant 1. This is a point in quadrant 1. So for the purposes of this particular problem, we can say that we only need the positive version. In fact, let's just check. It looks like, yes, both x and y look like they are positive numbers because they are in quadrant 1. So square root of 2 over 2, comma, square root of 2 over 2, that is the answer to that part. So we answered 3 questions. This one just took a bit more work. And this is the terminal point associated with, just to remind you, this had t equals pi over 4. So for that t value, we get this terminal point. So what we just did were a few different t values, and we get different terminal points. And I'd like to show you a little list here of common terminal points. Okay? Some of them are going to be ones that we've already done. So I'm going to list some values of t and what the terminal point is that you get with that. So let's make a little table. Here's t, and here's the point that you get. So I'll show you, I think, 5. We're going to do 5, 5 values of t that are pretty common. 0, pi over 6, pi over 4, pi over 3, and pi over 2. I did those in ascending order. You know, this is from smallest to largest, right? 0. And then pi over 6 is pretty small. Pi over 4 is a little bit bigger. Pi over 3 is a little bigger. Pi over 2 is a little bigger. Okay, 0. What would it mean to go 0? Like, we start at 1 comma 0 and we travel a distance counterclockwise. We travel a distance of 0. If you travel a distance of 0, you haven't gone anywhere, and your terminal point is still the starting point. Okay? Let's skip a little bit. Let's skip to the one we just did. We just did this was the square root of 2 over 2, comma, square root of 2 over 2. We also did the last one. The pi over 2 one was one of the examples up above, and we found the answer of 0, comma 1. Now, the other two I'm going to tell you for now. We could actually derive the other two in a similar kind of argument to what we kind of did up above. Pi over 6 and pi over 3 are actually going to have similar looking answers. This is going to be the square root of 3 over 2, comma, 1/2. And this is going to be 1/2, comma, square root of 3 over 2. Now, we didn't really find those from scratch. However, let's look at this fourth point here. That fourth point should look familiar because we did find this point earlier. Earlier, I said, what point would we get on the unit circle if we had x equals 1/2? Let's see if we've still got this back here somewhere. Remember when we did this? We got 1/2, comma, square root of 3 over 2. So I'm saying 1/2, comma, square root of 3 over 2. We already know that that is a point on the unit circle. The new thing that I'm saying now is that that point happens to correspond to a t-value of pi over 3. So it's good to know this table. It's good to know these common points. We're going to need to know other points as well. Is there a quick way that we can remember this? One thing I would say is you could notice that there's some pattern or some structure to this list. Let's see. What if you just look at the left-hand coordinates, like the x values? It goes 1, square root of 3 over 2, square root of 2 over 2, 1 over 2, 0. So they're decreasing. Okay, so it starts at 1 and it kind of works its way down to 0. And then on the other side, it's the other way around, right? It's because we've got the 1 here. Here's a 1, square root of 3 over 2, square root of 2 over 2, 1/2, 0. Here's a cool little trick that I like. I'm going to say that this can be thought of as, just because I like to show patterns in math, you know, that these numbers, they're not arbitrary. There is a pattern or a structure to this. It's up to you whether you want to try to remember it this way or not, but I want to say that all of these points can be thought of as involving square roots of things over 2. Watch this. Square root of something over 2, square root of something over 2, all of them. I'm just going to fill in the numbers afterwards. How about that? Square root of something over 2, square root of something over 2. This is just a pattern I like. What would have to go under those square root symbols in order for this to make sense? Let me just give you a chance in case you're writing that. Okay, so in order to match up with these points, what would have to go in here, in these empty spaces? All right, are you ready for this? Let's do the x-coordinates. Let's go from top to bottom, x-coordinates. In order to match up with what we said over there, it's actually going to go 4, 3, 2, 1, 0. Can you see that that equals these x coordinates? And then the other column, the column of y coordinates, we could start up here at the top and work our way down. 0, 1, 2, 3, 4. So that's a cool little pattern. I kind of wrote that off to the side, and you know, it's up to you if that helps you remember the structure behind this little table of common values, then great. Or you could just remember the points. You know, you could just remember them as is. You do also have to remember, like, which t-value do they go with. Notice that we've got pi over 6, pi over 4, pi over 3, pi over 2. So you kind of have to remember which of these t-values show up. Anyway, I thought that was cool. This 4, 3, 2, 1, 0, and this 0, 1, 2, 3, 4. Math is full of patterns everywhere. There are other t-values we could look at, of course. I mean, this is 5 t-values, but we've already looked at other ones. We've looked at 2 pi, we've looked at 2.5 pi. We get to other places on the circle, potentially. Let's move this up. So these are some small t-values. We looked at some larger ones like 2 pi and 2.5 pi. Here's a note. What do you think we do if t is negative? Is that allowed? Do you think that t can be negative? If t is negative, it's simple. We just go clockwise. We go in the opposite direction. Because in math, when something goes, you know, from positive to negative, it's really like you're going in the opposite direction. So I'll show you an example. Let's find the terminal point. And this time I'll have 3 of them again. This time I think I'll do the first 2 and then maybe ask you to do the last one. Let's do negative pi over 2. Let's do negative pi. And then I'm going to ask you to do t equals negative 5 pi over 6. That's going to be a tricky one, I'm warning you. But I'm going to ask you to try it before I help out with it. So let me help with part A and B first. These are all negative t values. So for part A, we'll draw a scratchwork unit circle, and we will think about starting from the usual starting point, except this time we're going to travel a distance of pi over 2 in the clockwise direction. I mean, earlier we had, you know, pi over 2 in the counterclockwise direction. So clockwise direction is that same distance, but in this direction, and that's going to take us down here. So it's like t equals pi over 2, but in the opposite direction. So instead of taking us to the top of the unit circle, it takes us to the bottom of the unit circle. Terminal point 0, comma, negative 1. Okay, I'm going to do part B also. Scratchwork unit circle. I think we talked earlier about what would happen if you went a distance of pi. This is going to be like t equals pi, but in the opposite direction. Do you remember how far t equals pi would go around the unit circle? I mean, it would go, t equals positive pi, it would go counterclockwise. It would kind of go halfway around the circle and stop. This time we are going this direction, halfway around, and stop. And that takes me to a terminal point of -1, 0. Now, I kind of warned you, part C is going to be the tricky one, but I'd like you to take a minute and try part C. Maybe pause the video and see what you can come up with. You might need to use something about pi over 6. That's my hint. Something about pi over 6. Okay, so why did I say something about pi over 6? Well, in that list of common terminal points, we look at this and we say, what's the closest thing that we've got that kind of looks like 5 pi over 6, Well, I mean, we have something over 4, something over 3, something over 2, but the pi over 6 one, that might come in handy, knowing what terminal point is associated with pi over 6. All right, so how about we label some things? Where would pi over 6 even be? So, like, if we went all the way around is 2 pi, right? If we go halfway around, that would be a distance of pi. Whether you go clockwise or counterclockwise, going halfway around. All right. What I'm going to do is I'm going to divide up the top half and the bottom half into what looks like pi over 6 increments. So that means chop it here, 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 here. So can you see what I did here? I made, like, this is pi over 6. And this is like 5 of them, right? So it's like go pi over 6, go another pi over 6, another pi over 6, another. If you do 6 of them, then you've gone pi around the unit circle. If we think in the other direction, maybe we say this is negative pi over 6. Got this, this, this. This is if we've gone 5 of them. Okay. So we want to know about this terminal point. We want to go here. And it takes us to something, comma, something. How about this? On the list of common terminal points, we had this point right here indicated as being square root of 3 over 2, comma, 1/2. Okay? And I think that the place that we're trying to wind up is the complete opposite side of the world from this point. Opposite side of the planet. So can we somehow use this to our advantage? We want this, but on the opposite side. I think that I could say we could probably figure out a bunch of points based on this one. Like, for example, if I took this point and I flipped across to this quadrant, can we figure out the coordinates of this point? If we flipped from this point to this point, wouldn't we just take the x-coordinate and put a minus in front of it? So it'd be like minus square root of 3 over 2, comma, 1/2. So that would be the point going there. If I start with this one that's in quadrant 1 from the list of common terminal points, what if I flipped down to here? Can we figure out the coordinates of this point? Well, if we flipped vertically, wouldn't we just change the 1/2 to a negative 1/2? Okay. What we want is over here. And you could take one of these 2 points and use it as a starting point, I guess. How about we look at this one up here, the one that's in quadrant 2 in the upper left. We've got negative square root of 3 over 2, comma 1/2, and we want to kind of flip that vertically. We want to keep the same x coordinate, the negative square root of 3 over 2, but we want to change the y coordinate from 1/2 to negative 1/2. All right, so it's a little tricky, but the point that we wound up with, by that kind of reasoning, we wind up at this point, which looks very similar to, trying to show this at the same time here, doesn't that look very similar to the terminal point associated with pi over 6? But instead of positives, it's negatives. Okay. Okay, so let's talk about this a little more, but that is the answer. Let's talk a little bit about quadrants. Haven't I been talking about quadrants already? I've been saying, you know, this is in quadrant 1, this is in quadrant 2. So remember, in general, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. They go in that order. Hey, look at that. They kind of go counterclockwise, which is what we've been doing when t is positive, at least. Counterclockwise is the direction we're going. And I want to say that for t equals negative 5 pi over 6, we used the corresponding terminal point from quadrant 1 I feel like to solve that problem, I used what we knew from that list of common terminal points. That list of common terminal points is entirely in quadrant 1. And what I'm saying now is that you can use those to help you figure out things that are in the other quadrants. Quadrant 2, quadrant 3, quadrant 4. Let's make this a little bit more formal, because what we just did seemed like we had to kind of piece it together and use some reasoning, but there is kind of a method behind this. So, definition. If you're given t, the reference number going to underline that, t with a bar over it, sometimes that would just be pronounced t bar, is the shortest distance along the unit circle between the terminal point determined by t and the x-axis. For example, t equals negative 5 pi over 6 has reference number t bar equals pi over 6. Let me give you a chance to write that. So let me go back and show you something here. So you can see the definition, and you can see the picture that we had for part C over here. we were interested in negative 5 pi over 6. That was the t-value we were interested in. So what's the reference number? The shortest distance along the unit circle between the terminal point determined by t and the x-axis. So here's the terminal point. Watch this. Here's the terminal point. Here's the x-axis. It's this little distance right here. Let me see if I have another color. How about we highlight it? This distance. I don't know how that shows up on the projector, but that distance that I just highlighted, that curved distance, is the shortest distance along the unit circle between the terminal point that we're interested in and the x-axis. And that distance is, in this case, pi over 6. Okay? In some other problem, it might be something else. Now, if we are given t, we can use this reference number, t bar, to find the terminal point. And I'm going to be describing kind of what we just did, but in a more formal way. We're going to break this into 3 steps. Step 1, find t bar. To find t bar, you might need to draw a picture, and you might need to figure out what that distance is. I don't want to cover this up, but the distance that I highlighted, you might want to, find out what that is based on the picture. Step 2. Find the terminal point A, comma, B determined by t bar. That's not the final answer that we want. We want the terminal point for t. This is assuming we're given a t value. We want to find the terminal point for t, but along the way, we find the terminal point determined by t bar. Step 3. This is the last step. So the terminal point determined by t, this is what we really want, is some form of plus or minus a, comma, plus or minus b, where signs are chosen based on quadrants. Say quadrant. There we go. I'll give you a chance to see that. We're going to do another problem, and we're going to use this 3-step process. Before we do the other problem and completely move on and move pages and stuff, I want to show you one last time the problem that we did. I would say that we kind of did use the 3-step process. We were given a t value. We want to find the terminal point associated with this t value. I suggested that my hint to you was that there was going to be something based on pi over 6. Well, the idea is that this distance right here is pi over 6. Now we are calling that the reference number. So that's step 1. Step 2, find the terminal point for t bar. That's this thing right here, square root of 3 over 2, comma 1 over 2. Step 3, the final answer to the problem will be some form of this, but possibly with pluses or minuses. And what did I say the answer was? I said it was square root of 3 over 2, comma 1/2, but it has minuses Why are there minuses? It's because the point that we're looking for is in quadrant 3. Every point that lives in quadrant 3 has a minus in front of the x-coordinate and a minus in front of the y-coordinates down here. Let's do another problem. Let's do a fresh problem. We can forget about that pi over 6 stuff. Okay, I'll talk us through this one. Example, given t equals 7 pi over 4, find the terminal point. Now, I think we might draw more than one unit circle for this problem. That's okay. You just think of them as scratch work. Step 1. Step 1 is to find t bar. So here's what I'm going to suggest. Let's draw a unit circle. When all else fails, draw a unit circle. When you don't know what to do, draw a unit circle. You know where we start from, right? Start from the usual place. We want to go around counterclockwise a distance of 7 pi over 4. How do we know how to stop? How do we know, like, how far that is? Can you see that 7 pi over 4 is almost as big as 2 pi? 2 pi would go all the way around, and all the way around, get back where we started. This is almost that big, because that would be 8 pi over 4. This is 7 pi over 4. How about this? Let's chop up the unit circle. Maybe this will help. Into portions of pi over 4. How many portions of pi over 4 are there to make up the whole unit circle? Well, this would be pi over 4. This would be, do we want to label all of them? Let's do that. 2 pi over 4, 3 pi over 4. I'm going to zoom in on this, because I'm writing small, so I'll zoom in. Can you see that this is 4 pi over 4, also known as pi? This is 5 pi over 4. Here we've gone another one, 6 pi over 4. And here we've gone 7 pi over 4. And if we go one more, then we've gone 8 pi over 4, and we've gone all the way around. So let's just stop there. I'm also going to label the quadrants just because we'll see if that helps. 1, 2, 3, and 4. Okay. So what we're trying to do is we're trying to go 7 pi over 4 around. So we're going pretty far around the unit circle, right? Almost all the way around. But stop here. This is the terminal point determined by t. We want to find the coordinates. This is something, comma, something. Can you see what the reference number is? This is supposed to be step 1. The shortest distance along the unit circle from the terminal point to the x-axis. So which way would we go to get from here to the x-axis? We would go here. That's the shortest distance to the x-axis. That length this length is, what do you think? Pi over 4. Pi over 4. So we found that t bar is pi over 4. That was step 1. Find t bar. I'm going to zoom out. Let's do step 2 over here. Step 2. Step 2 is to find the terminal point determined by t bar. So this time I don't even think I'm going to draw a picture for this. I'm just going to say t bar equals pi over 4 goes to. This was one of the common points on our list of common terminal points, common t values. We also said this earlier, I think, as one of the problems that we did. But basically, if you go pi over 4, you stop at this terminal point. One more step to go. let's just look. What does it say up here? Step 3 is going to be the terminal point determined by t is some form of this, but we have to figure out whether it gets a plus or a minus for the first coordinate and a plus or a minus for the second coordinate. I think you might even be able to tell just by looking at what's right here. Let's answer, maybe we can just answer it right here. Step 3. T goes to, and I wrote t, not t bar. T goes to some form of plus or minus square root of 2 over 2, comma, plus or minus square root of 2. We just need to figure out, is it plus or is it minus? We're looking at this point. It is in quadrant 4. Quadrant 4 has all of the points in quadrant 4 are always going to have a positive x value and a negative y value, right? Think of any point that's down here. It's down here, so the y value is negative. It's over here on the right half of the picture, so the x coordinate is positive. So the answer is, it's the answer we found above, but with a positive for the first one and a negative for the second one. Square root of 2 over 2, comma, negative square root of 2 over 2. And let's put a box around that. You can take one last look at the picture and ask yourself, does that make sense? Yeah, I think that makes sense. Positive x value, a negative y value, square root of 2 over 2, comma, negative square root of 2 over 2. I'm going to move the page, and we'll do one more thing. Let's draw a big unit circle here. Okay. Based on what we've said today, I'm going to move the other page completely away in a moment, so get ready for that. Let's draw a big unit circle. Can I make a nice circle this time? Yeah, not bad. Not bad. Okay. We can work with this. Based on what we've said today, I'm going to label some points and some t values. You know that sometimes when we do these, I've been kind of labeling the t value on the inside. Let's kind of do that. Let's label like the t value on the inside. This is a t value of pi over 2, and I'll label the point on the outside. It is 0, 1. So if we went from the starting point, a t value of pi over 2, we would go to here and stop. This shows you the t value and the terminal point. If we went further, if we went a distance of pi, that would take us to -1, 0. If we went a distance of 0, that keeps us here at the starting point of 1, 0. Let's fill in those 3 points that were on the list of common values. So one of them is here, it's pi over 4, and it was the square root of 2 over 2, comma, square root of 2 over 2. That one's easy to remember because the x and y are equal to each other. Some of the other common values are here and here. One of these is pi over 6, and one of these is pi over 3. Which one is which? Pi over 6 is the smaller number. So pi over 6 is here, pi over 3 is here, and the values were root 3 over 2, comma 1/2, and this is going to be 1/2, comma root 3 over 2. Right, so based on what we've said today, we could actually fill out a lot of points. How about the one that we just found in the problem we just finished? If you go 7 pi over 4, we found that that had an answer of square root of 2 over 2, comma negative square root of 2 over 2. That was the answer to that problem. Where was that other one that we spent a while on? That was that negative 5 pi over 6. That was kind of over here. You know, there's kind of two ways to think of this point. We were talking about this one as part C to a problem earlier, where we were getting here by doing t equals negative 5 pi over 6. We would go this way and stop. You could also think of it as going counterclockwise with a positive t value and stopping here. If you did that, you might think of this as 7 pi over 6. And this takes us to negative root 3 over 2, comma negative 1/2. Okay. How about we didn't label this point down here? I know that this point down here is 0, comma negative 1. Can you think of what t value this would be? That's a good question. What t value corresponds to this terminal point? Think about that for a second. Okay, I'll tell you how I get it. Over here, t is 0. Over here, t is pi over 2. So it's like we went pi over 2, then we go another pi over 2, then we go another pi over 2. So we've gone a total of 3 pi over 2 to get here. Do you think you could label more points? I bet you could. I bet you could label this one here. I bet you could figure out the coordinates of that. It's kind of like this pi over 4, except it's in a different quadrant. So maybe you would use a reference number of pi over 4. Maybe it would have these same numbers, but maybe with a plus or a minus in front. I bet you could do the same to figure out this point here, this point here. You could figure out these using reference numbers of pi over 6 or pi over 3. I think you could label all of those points. I think you could find the t values and you could find the terminal points. Based on what we know from quadrant 1, you can figure out these other ones. All right, and you should be able to do that. Going forward, that is going to be a useful skill to have, to be able to like fully draw a completely labeled unit circle and just know these points pretty quickly. So in upcoming sections, if you need to know what terminal point goes with pi over 3, you should be able to know it very quickly. What if I said 2 pi over 3? Can you figure that out? You would want to be able to figure out what that terminal point is. What if I said negative pi over 4? Or negative 3 pi over 2? You should be able to figure out what those terminal points are. Okay. And it's not just about memorizing them, although I guess there is a little bit of memorization involved with these quadrant 1 points. So that was the section about the unit circle. Yes, there is a little bit of memorization involved in this chapter, you know, but we'll try to keep it manageable. You know, if you know those points from quadrant 1, you can figure out quadrant 2, 3, and 4 as long as you have a good understanding of how this all works. So I want to address one thing before we turn this off, and that is that I said that this topic, the unit circle, was going to be our beginning of trigonometry. And some of you may have seen some trig before. Um, you know, it's not necessarily a prerequisite for this class. Some of you may have seen it, some of you might not. But I want to just say that everything we talked about today, you might look at it and say, is that really trigonometry? Because we didn't talk about triangles. In fact, I don't think we even used the word angle. I don't think we talked about angles at all. I don't think we said anything about a 45-degree angle or, 90 degrees or anything like that. That's okay. Everything we did today is still a part of trigonometry. We're just sort of looking at it from a different perspective. We're looking at circles, and then in the next video, we're going to start talking about angles. Or maybe not. We might actually save angles. We might actually save angles for even a little bit later. We'll see. But we're going to continue talking about circles for a while before some of those other things come in. Okay? So that's it for today, and I hope everyone is doing well, and I will see you soon.